for a second. So while she is, there's the answer to the question. So I don't know the exact answer off the top of my head. I'll need an engineer back to answer that with my
어,
point during the course of its orbit around
안녕하세요.
the sun. So
이제는
the
그러네요.
telescope essentially orbits
저
the
일단
sun
퀴즈
in line
들어왔고요.
with the Earth, and it takes, of course, a year
어쨌든 뭐
to make
합니다.
that orbit around the Earth or around the sun along with the Earth. But then, yeah, along the way, it's making this long, big circular orbit around the L2 point.
Great. Thank you so much for that. And when Scarlett comes back, Kevin, we will be sure to see if we can get the answer to this question for you. So let's move on. We have Stan on Facebook, Amber, that's got a great astronomy question. He wants to know, could you tell us a little bit more about the decision-making process involved with selecting Webb's targets and who decides the priority and allocates time for each of these points of interest?
That is a great question. And the answer is that it is purely sort of democratic. Anyone in the world can propose their best idea on where to point this telescope. That's how it works with Hubble right now, and that's how it's going to work with JWST coming up in the very near future. So basically, once a year, astronomers from around the world sort of get together and think up their best ideas of where to point the telescope so that we can, learn new things about the universe. And they write proposals, submit the proposals, and then another team of astronomers reviews the proposals and sort of ranks them. And this is all done anonymously. So there's, striving to be fairness in the process so that at the end of the day, the best ideas get prioritized, and that's who gets time on the telescope. Now, the really great thing about this data that's going to come back from JWST, same thing with Hubble, is that a lot of times the astronomers who win time get a certain amount of proprietary time. So they get access to the data for 6 months, maybe a year. But after a year, it all becomes public. So anyone in the world can use that data to do science, which is awesome. And then a lot of the data that's taken during the first year of JWST's lifetime, particularly during the first few months, is going to be available immediately to everyone.
Wow. I mean, there was so much awesomeness in that. It's so cool to hear that Webb's data, this was already such an international mission, and that this incredible piece of technology gets to be used and the love is shared by everyone around the world.
자,
And
지금까지
to
제가
actually
정리해가지고
follow up to that,
정리해드리겠습니다.
talking about what
죄송합니다.
objects that James Webb will be looking at and some of its
지금
targets.
사이언스 라이브를
Steve
하고
on Twitter
있고요.
is wondering, will JWST look at objects in our own solar
사이언스 라이브를
system
하고 있습니다.
as
그래서
well?
제가
Absolutely. So JWST has the ability to look at objects from Mars on out. So it can, of course, again, it's orbiting just outside the orbit of the moon. It's about 4 times further away than the moon. So it always has to be pointed out towards deep space. It can't ever look back towards the Earth. So, for example, it could never observe Mercury and Venus, but it can observe Mars and everything on out. And in fact, during that first year of observations, we have detailed plans to look at lots of objects in our solar system, from Mars, some of the moons of the outer planets. So there's a whole list that you can find online of objects within our solar system that JWST is planning to study during that first year.
Nice. And you say that we can look
이거 지금
online.
어떻게
Is
뭐
there a
하냐면은
specific website that people should look forward to find
앞으로
this
제임스
information?
웹을 어떻게 이용하냐, 그 과학자들이 어떻게 이용하시냐, 그 얘기를 지금 하고 있습니다. 그래서 1년에 한번 천문학자를 만나서 제안을 하고, 다른 천문학자는 이제 그것을 이제 그 제임스 웹을 같이 이야기하고 많은 경우 시간을 할애할 수 있다. 그리고 독자 데이터 엠바고는 최대 1년이다. 이야기를 하고 있네요.
Or you can just Google JWST Cycle 1. So we call the cycles year by year. So Cycle 1 observations are what that first year is going to be.
Thank you so much for sharing that. I know a ton of viewers are going to be excited to hear that because that is a question we get so often on social media.
근데 일정이
So,
이거 말고
Amber,
지금
we have
또
another question from Facebook.
한
Danielle asks,
7시쯤에
is
또
the
하나에 또
exposure time in
하나 또 이게 또
infrared
얘기가
different than it is in visible light for data acquisition?
예정이 돼 있습니다.
Absolutely. So the wavelength of light that you're looking at always does come into play when you're planning these observations. And that's for several different reasons, but one of the fundamental reasons is just because objects in the universe
지금
emit these different wavelengths of light at sort of different strengths. Okay, so you can think of one object might not be very bright in the visible light, but might be in emitting a lot of infrared light. And in fact, some of the things we want to look at with JWST are going to be great to observe with this telescope for that specific reason, that you can't really see them in visible light or other wavelengths, but you can see them in infrared light. And so yes, because objects emit at different sort of power at different parts of the wavelength range means that we'll have to sort of calculate those different exposure times. And you can see right now, actually, one of the things I love
그리고
about
이제
these
지정된 온도 범위에 도달한 다음에는 그 거울의 세레모니를 준비해야 된다. 그래서 5월달에 5개월 안에 첫 번째 관찰을 기대하고 아름다운 이미지와 놀라운 과학을 기대하고 싶다.
And this is a near infrared image of the Eagle Nebula, or often called the Pillars of Creation from Hubble. And what infrared light allows us to do is essentially peer down into those dust clouds.
제임스 우주망원경은 전기성 방향을 저격을 잘 볼 수 있고 가시광 센스는 볼송도들을 볼 수 있습니다.
So when people
이야기를 하고
ask these
있습니다.
pictures are going to be pretty, I always point them to this image because this is like a beautiful, spectacular image.
I completely agree. And oh, hey, Scarlett, so glad to see you back and online.
Technical difficulties.
No worries at all. Amber, I'm going to
그리고
toss you
제임스
one more
웹
question, kind of in the same light.
수성, 금성, 지구를 볼 수 없지만은
to know that due to Webb's position at L2, is there anything we
그
won't
태양계
be able
화성하고 태양계 바깥쪽 목표를 관찰할 수 있다고 합니다.
Yeah, so
외행성계를
I touched on this a little bit,
외행성이 관찰할 수
but
있다.
because it is at that part of space,
이야기를 하고 있고요.
and because it's an infrared telescope, of course, the mirrors always have to be pointing outward, away from the sun. We can't ever point the telescope back towards the sun because that would essentially fry our detectors. And so that means we can't look back at the moon, the Earth, Venus, Mercury, or the sun itself, of course. But everything else from the orbit of Mars on out is fair game for this telescope.
Wow. I mean, that gives us a lot to look at. Thank you so much. And so, Scarlett, Amber was just telling us a little bit about what we can expect for Web 2 image and how that process really works between the infrared and the visible light. But we have a question from Mike T on YouTube who asks, how long does it take for communications to transfer to and from the telescope? Do you have any insight on that?
Well, that's a very specific question. I would probably have to defer that one to the comm team, but we use these massive, powerful antennas from the ground to relay the signal from the computers in the Mission Operations Center to the telescope. So from the control center, we are sending commands to the telescope. Any activity that it performs, we're commanding from the control center. And then once the telescope performs what it needs to do, we are monitoring real-time telemetry down on the ground.
Wow, thank you. And so back to just monitoring this telescope systems, and a little bit earlier you mentioned that in the immediate future, the next 5 months, Webb will need to cool down to a specific temperature in order for its instruments to work. And so we have Anthony on Instagram who wants to know specifically how much time till Webb actually cools down to this correct temperature.
Right. So it's about 40 Kelvin. I believe it takes about 98 days for the instrument's mirror to cool down to temperature.
Wow,
good question.
That is very cold. That is very cold. Thank you. And so Yeah, and a follow-up, Twit app on Twitter asks, has the gradual cooling down of web over the last week been according to the simulations? Has it happened as y'all thought it would?
Yeah, of course, it's never perfect because it is a simulation. But yes, it has been almost just as expected. We have had our cooling rate increase quite a lot from the deployment of the Sun Shield, and everything is going marvelous, really.
Nice. I mean, that is what we love to hear and hope it continues that way over these next 5.5 months, fingers crossed. And so another question we have is from Justin on Twitter, who asks, are there other observatories in L2 besides JWST?
잠시만요. 진짜
Scarlett, you
컴퓨터가
want to
좀
take this one?
안 좋아서.
Amber, do you want to take this one actually?
Sure. Yeah. So there are other observatories out in this part of space. There's the European Gaia Observatory is out in this part of space, and in fact, we've been able to learn about, for example, the micrometeorite situation in that part of space, thanks to some of these other satellites. So that's a question I get a lot is, are we worried about micrometeorite impacts in that part of space? And the short answer to that is no, not really, because it's a semi-stable point. Stuff doesn't tend to collect there. But part of the reason that we know that for sure is because we've been able to sort of assess it from other spacecraft that are in that part of space. So yes, we do have other satellites out in that part of space.
Nice. Thank you. Thank you so much for that. And thank you too to everyone submitting your questions today. If you are just tuning in, we really encourage you to participate live in today's show by dropping a question in the chat stream wherever you're watching from, or by using the hashtag #UnfoldTheUniverse on social media. Scarlett, Amber, don't go anywhere. We will get back to you in just a second. But first, we have another way for those watching to participate in the Webb mission. We know that 5 months is a long time to wait and wonder about what Webb will discover. Show us what you believe the Webb telescope will reveal by creating art. You can sing, you can paint, you can dance. The universe is literally the limit in this case. So share a picture or a video of you and your creation online using the hashtag #UnfoldTheUniverse. You'll have a chance to be featured on NASA's social media page and also the NASA website. Take a look at how it works.
Hi everyone, I'm Kelly Girardi, and this is Delta V, and we're kicking off the Unfold the Universe Challenge with NASA and the James Webb Space Telescope.
The Webb telescope is NASA's biggest and most powerful space telescope ever. It's going to help reveal our universe like never before.
Delta, what do you think we'll discover?
I think we'll see stars, planets, and galaxies. I can't wait!
NASA is hosting an Unfold the Universe art challenge. Use your imagination to share what you believe the Webb telescope will find. It could be a drawing, a poem, a song. You could be creative.
그래서 들어갔습니다. 죄송합니다. 제가 일어나지 못해가지고 알람 맞춰놨는데.
Wow, Delta, it's beautiful. I can't wait to see what everyone else comes up with. You can share a photo or a video of your art and what you think Webb will discover using the hashtag #UnfoldsTheUniverse.
Go, Webb, go!
I love this art challenge so much. I have had the amazing honor of being one of the people that gets to sift through some of these submissions, and each creation has been so incredibly unique and really just showcased people's individuality. It's been inspiring to see everyone's wonder and creativity from around the world, people of all ages and from so many different countries. For everyone that has already contributed, thank you. Who knows? Maybe your creation really will be what Webb reveals. So keep them coming online. You can submit them using the hashtag #UnfoldTheUniverse. We love to see them, so we encourage you to join. Okay, let's bring back Amber and Scarlett because we still have so many great questions coming in online. So the next question we have is a person on Twitter who asks, will JWST look at the Hubble Deep Fields? Amber, this is a perfect one for you. Will they be able to see it?
Yes, absolutely. In fact, one of the primary drivers for building JWST back, years ago, a couple of decades ago, was to be able to find the very first galaxies that were born after the Big Bang. And by looking at images like the Hubble Deep Field, Ultra Deep Field, we've been able to push back and see very distant galaxies. But at some point, we sort of come to the edge of what Hubble can see. And JWST was specifically designed to help us find those first galaxies beyond what Hubble is capable of seeing. And the Hubble Ultra Deep Field and some of the other deep fields that Hubble has observed are these places in space that are incredibly rich in data. So not only do we have data from Hubble, we have data from other observatories. We have X-ray data from Chandra. We have infrared data also from Spitzer. And so all different kinds, all different wavelengths of data in these fields. And so the fields themselves are incredibly rich, and adding JWST's deep infrared data on top is going to help us both hopefully find those very first galaxies to be born over 13.5 billion years ago, as well as just add to the depth of knowledge that we can learn about galaxies and about galaxy evolution in these very rich fields.
Wow. I mean, you mentioned 13.5 billion years. It is just incredible what this telescope can see. And so we've talked about Hubble Deep Fields. We've talked about some of these first observations. And that leads me to a really great question from W.F. Swigert on YouTube. Scarlett, this is a great one for you. Are the mirror alignments and adjustments intended to be permanent, or will they need to be some adjustments depending on what Webb decides to look at?
Yeah, so it's designed to be adjusted anytime that it needs to be. So we will have to align them throughout the life of the mission. So it's not just right now. It's a continuous process just to make sure that they're always perfectly aligned.
Wow, it's really like we really do have our own little transformer in space. That's so cool. And so... Oh, I have a great question for both of you. Emma Fitzpatrick on YouTube states, "Hi, my 10-year-old son, Dara, is an inspiring engineer and is really inspired to watch you tonight. What advice would you give for him to someday work on projects like this?" Scarlett, as our engineer, do you want to kick it off?
Sure. I would say work very hard. Don't give up. Engineering can be hard for a reason, but then we get amazing gifts like JWST. So it's always worth it. Just continue on your path. Make sure you have a great support system. And like I said, never give up. Reach for the stars.
I love it. And then Amber, we also have a lot of aspiring scientists. Do you have any advice for anyone out there who might want to follow your footsteps one day?
Yeah, well, Scarlett just gave some really great advice, and I think that holds for science as well. And one specific thing she mentioned that's been really important for me is that support network. So I know that mentors have been incredibly important to me to help me, get to where I am in my career. And so I think it's super important to find people all along the way, no matter what stage you are in your education and your learning, to find people that are willing to help you and support you and sort of help you make it to the next step, because none of us do any of this by ourselves. It's a group effort for sure. So find good mentors. That is probably my top piece of advice. And then if I could jump back to a previous question, because I now have an answer. So one of our engineers texted me, thank you, Mike Menzel, and said that the time it takes to orbit L2 is 180 days, which I didn't know until just now. So it actually takes half a year almost to make that full complete orbit around L2. So I knew it was a long time. I didn't quite realize it was that long. So super interesting.
Yeah, wow. Thank you for that. And thank you, Mike. And so moving on, we have a great question from Penny on Facebook. Amber, if you want to take this one, feel free. She wants to know, how will the public access the images once they're acquired?
Yeah, so that's a great question. That also will be housed at the Space Telescope Science Institute, which is where Scarlin works. So they are our sort of repository for housing the data for the telescope, also for Hubble. So that will be the place to go to get all of the images. And of course, as we make discoveries, as astronomers make discoveries along the way with the data, we will, of course, provide those fully produced beautiful images to the public as well on all of NASA's channels.
Great news. Thank you, Amber. So our next question comes from Connor McEwen on Facebook, who asks, will the JWST correct for photons from the sun pushing on the sun shield? Scarlin, do you have any insight on that?
We will get a lot of solar pressure, solar radiation pressure on the sun shield. But as far as the photons and all of that, I think Amber would probably be
여기 나온
a
것처럼
better
지금
source.
첫 사진은 한 여름쯤에 나오겠다 이렇게 지금 이야기를 하고 있죠.
Radiation will push on us. So that's, the sun shield is essentially a solar sail. So yeah, we will make small corrections during the course of operations to make sure we sort of offload that momentum that builds up due to solar radiation on the sun shield. Yep, that's going to be a regular part of our operations.
그리고 예전에 했던 것들 잘 정리를 해주고 있습니다. 어떻게 지금 구성이 되는지. 선실들은 이제 세스 코트 크기에 5겹 5겹 돼 있다.
New technologies really built for this telescope. We have a question from Brent on Twitter who asks, what are some other new technologies that building the JWST telescope has created, especially transformative tech? That might have changed our daily lives. So basically, he's looking for spin-offs. Has any other new technology been created through the building and operation of Webb?
기억이 좀 안 납니다.
Scarlin or Amber? Whoever wants to go first.
That's a great question I'm curious about.
Yeah, so the one that comes to mind that I know of that I know NASA has talked about is the fact that because these mirrors have to be aligned so precisely, the shape of the mirror has to be absolutely perfect. And so that'll happen after this upcoming 3-month mirror alignment process. So if you can imagine if the whole 22-foot mirror was the size of the continental US, the biggest bump on this mirror is going to be about 1 inch or 2. Okay, so it's very, very smooth, the surface of the mirror. Now, it turns out that confirming that smoothness and even measuring the smoothness is really, really hard to do. And so just the technology that we had to develop to measure the smoothness of the mirror has actually already been used in the medical field, in the field of ophthalmology. So eye doctors have used this technology to help measure the shape of the human eye. And this has already gotten benefits in making eye surgery much shorter, much more efficient, and much safer. So that's one example of a sort of spin-off technology that's come from the development of this telescope that really plays real effects in the real world.
Wow, that is really cool. Thank you, Amber. And to kind of stick on this topic of mirrors, Scarlin, we have a question from Brian on YouTube who asks, who's looking for more clarity about where Webb's 18 mirror segments are supposed to be pointed. Specifically, he's wondering, are all 18 segments pointed in 18 different directions or pointed in one direction and aimed at and targeted at different focal points?
Yes, that's a great question. So they all the 18 segments have to be aligned to make that parabolic, that iconic picture that you've all seen. It's a bit of a concave mirror there. And basically they all have to be pointed in the same direction. The light is going to be reflected onto the big giant mirror, and then it will be that will beam into the secondary mirror of the telescope, which will then go back into kind of like that nose in the middle of that giant mirror, which holds the tertiary mirror and fine steering mirror. And so yes, it's that parabolic shape that you see there. And that's what we need to maintain the entire time. The pointing is done with our attitude control system.
Okay, great. So yes, the mirrors are all actually pointing in the same direction. Thank you. And so moving on, we have a question from Manuel on Twitter who asks, can Webb's observation schedule be adjusted in case a discovery shifts
자막에도 지금 나와
scientific
있지만은
priorities?
앞으로 제임스 우주망원경의
Do you have any insight on that?
거울은 자, 사람
Yeah,
머리보다
absolutely.
더
In fact, that
얇은
sort of
거의
flexibility in
나노미터급의
scheduling
지금
is
정렬이 더
built
필요하다.
in.
지금 이제
And so
밀리미터급의
in
정렬만
astronomer
나왔거든요.
speak, those are
그래서
called
앞으로
targets of opportunity
나노미터급의
or TOOs.
정렬이 필요하다.
And so
여기서
if something
이야기를
super exciting,
계속 하고
something sort of
있습니다.
short-lived happens in the universe and we want to pause our observations and point the telescope in that direction, we have that flexibility built into the schedule to be able to do that. So a good example would be like if a supernova goes off, or some other event like that happens sort of quickly. So yes, we have that capability built in. There are some constraints on that. So you can imagine as the telescope orbits around the sun, again, we sort of talked about it can't ever look back towards the sun. So it can only see a part of the sky at once. And so if it just so happens that your object of opportunity is in the wrong part of the sky, we wouldn't be able to do that. But for the most part, in general, we do have the flexibility to sort of pause the scheduled sort of routine operations to observe things that happen in the universe that sort of happen all of a sudden.
So sticking on kind of these shifting in case of a discovery, Robert on Facebook asks, as part of Webb's mission, scientists will be analyzing the atmospheres of exoplanets on possibly habitable conditions. I know that is something a lot of people are very excited about with this specific mission. And so he wants to know, how will Webb collect this data of these atmospheres, and what kind of things will scientists be looking for specifically?
So the way that we study exoplanet atmospheres is by watching the planet transit in front of its star. And so this is how we've been able to discover so many of these exoplanets in our galaxy, is by watching a star and watching for the light to dim in a periodic way. And so that's how
앞으로
we
사진이
know
어떤
that a
사진이 첫
planet is
사진인지
orbiting.
모르겠는데
And so you see the
제임스
simulation
웹은
on the
앞으로
screen now. You can sort of see that teeny tiny little planet crossing in
외계행성
front
그리고
of the
행성들을
star. And you can even get a sense
외계행성들을
of just how
중심으로
hard this is. So
연구를
essentially what we're
하겠다
going to
지금
be
나오고
doing
있죠.
is watching that planet pass in front of the star and then watching the starlight filter through that planet's teeny tiny little thin atmosphere. It's really, really difficult, very difficult observations. But with JWST, we now have new capability to do this better than has ever been done before. I study how stars and black holes form in distant galaxies and how galaxies change over time. So exoplanets are pretty far from my own personal research, but I think that some of the exoplanet science that JWST does is going to be some of the most outstanding, surprising, incredible things that JWST is going to do. And it turns out that an infrared telescope is perfect for these observations because some of the things in these atmospheres that we really care a lot about happen to fall in the infrared part of the spectrum. So chemical signatures like carbon dioxide and methane and water vapor, all of those that could be sort of, pointing towards the building blocks of life.
Wow. I mean, that is incredible, Amber. Thank you so much for just painting that picture for us about how this is going to happen. And I think it's so cool to just go back to the fact that Webb is making all of these
그래서
observations
제임스 우주망원경은
at a stable
그
orbit at this
외계행성의
Lagrange point 2 in
그
space.
대기를
And so,
아주 관찰할 수
Scarlett,
있는 아주
this whole show we've
적합한
been
도구다.
talking about Lagrange point
지금까지
2.
여러 가지 그
I have a
제임스
question about that.
다른
How can you
외계행성 같은 경우는
even
저기
orbit
스펙트럼으로
an
의지해가지고
empty point
연구를
in space?
했었는데 좀 한계가 있었죠. 그래서 제임스 우주망원경은
So it's actually the reason we chose that location.
그래서 우리 말하는 경우는 앞으로
is
이제 그
because
외계행성
it was already explained in the
그
video
탐사에서도
what
굉장히 중요한 역할을 할
Lagrange
것이다.
2 is, but
이야기를 하고 있습니다.
because of the gravitational pulls, the telescope is able to float much easier in that orbit, and we don't have to use much fuel to maintain ourselves there. So that's basically the gist of it. And you're seeing that in the simulation there. And you see the telescope orbiting L2, orbiting around the sun there in this sort of halo orbit, not exactly a circular orbit, more halo.
Thank you for that. And so we have our next
저희
question
이사 왔는데
from
지금
Morali
그 오른쪽에
on
계신 분은
Facebook,
그
who
유로
wants to
우주
know, will James
소속
Webb provide
과학자입니다.
information about the Big Bang?
다 여성 과학자만
Amber, I think this is a great
뽑아가지고
one
아마
for you.
참석을 시킨 것 같아요.
Sure. So when we're thinking about, looking back in time, what the real thing we want to find out with JWST is to see the first galaxies that were born after the Big Bang. And so we won't be looking back, so to speak, to the very quote unquote moment of the Big Bang. But what we're really interested in seeing is how what happened in the Big Bang gave rise to those first galaxies. And that's a part of space that we've never seen before. So, of course, we've seen images of the sort of the glow, the remnant of the Big Bang in the cosmic microwave background. But at that point in time, there was no stuff, right? There was just radiation. There was just elements. And so what we're looking for is the point at which that early hydrogen and helium, what was the components of the Big Bang, when that hydrogen and helium first started forming the very first stars and galaxies, the first stuff in the universe, the first objects. And so that's what we're going to specifically be looking for with JWST, is this first epoch of galaxies that formed after the Big Bang.
Wow. And so, Amber, to get this right, we have never done that before, have we? We have never looked that far back.
Right. Yeah. So with Hubble, we've talked a little bit about the Hubble deep fields. And with the deepest images we've been able to take with Hubble, we've been able to see back pretty far and see some very distant galaxies and see those galaxies as they were in the very distant past. So we have been able to see very distant galaxies with Hubble, but we sort of come up to the edge of what Hubble can do. We can't see any further because these first galaxies are emitting their light. The light now is only in the infrared part of the spectrum. So even if we had a huge, visible light telescope in space, an even bigger one, we still wouldn't be able to see these galaxies because their light is now totally in the infrared part of the spectrum. And so yeah, we'll be able to see that first epoch of galaxies that's more distant than what we've been able to see with Hubble.
That is so exciting. Thank you. Thank you so much for that. And so we have a fun question for both of you. Scooby Arthur on YouTube asks, what are you hoping for the very first discovery? Scarlin, I'll kick it to you. And then Amber, would love to hear from you next.
I think for me, what's most fascinating is to think that now that we're going to be able to through all of the gas and fog and space that we weren't able to before, mid-infrared, that discover things that we didn't know existed. So that's super fascinating to me. Of the exoplanets, learning about other planets that are made of rock, like us, like Earth, that could have oxygen or signs of carbon dioxide, and us that could help support life. That's just interesting. And know about our origin, how we got here.
Yeah, and for me, Yeah, sort of in a similar vein. I mean, we have all of these very specific questions we want to answer about the universe, right? And we have this first year of observations planned where we hope to start to answer some of those questions. Things like, how did planets and stars form? And what's going on with some of the objects in our solar system? And again, all the way back to finding those first galaxies. So we have these very specific questions that we want to answer. But for me as a scientist, the thing I am most excited about is the discoveries that I know we will make that are completely unexpected. It's like there are these surprises out there lurking in the universe, things that we've never dreamed of. And I think we'll find those. And I think that prospect of finding things that completely surprise us, that sort of change the way we understand the universe, that is what I'm most excited about with this telescope.
Wow. Thank you both. I mean, I completely agree. And also, I know, Amber, you've done a little bit of work with black holes. And so just seeing what this telescope even reveals about those is going to be incredible. So much great science to come for Webb right now. So for Scarlett, I've got a question for you from AvGeek on Twitter, who asks, how excited does an aerospace engineer get about the astronomical aspects of a mission like this? And I can repeat that as well if you need it.
Super excited, even though you can't see it right now. I remember during the deployment phase, I was on the edge of my seat. It was like watching, the Super Bowl for me. And pop champagne while I was in the control center, but obviously that's not a good idea. But definitely when I got home, it was a big celebration. I'm really over the moon about how amazing everything has been going up to this point, and I'm so excited for the future.
Nice. And Amber, how excited does an astronomer get for the aspects of a mission like Webb?
Yeah, well, I mean, we're obviously excited about the science. Of course, all of us astronomers are. But for me, one of the coolest things about working at NASA is that we do work alongside these brilliant engineers that have built this awesome machine that is going to, I think, change the way that we understand the universe. And just to be a part of that, to be, to be able to walk across campus and see the telescope being built a few years ago really gave me a much better understanding. Again, as a scientist, it gave me a better understanding of just what goes into engineering, to building these types of things. It's absolutely incredible. I think this is a moment in our history as humans that we can just, as a society, as a species, be so proud of, because we've built this amazing, beautiful machine that is going to transform our understanding of the universe. And I think it's incredible.
So well put. Thank you both for that answer. And so, Scarlett, I have another follow-up for you. Glitched Robot on Twitter asks, what can you tell us about JWST's secondary mirror? Is it the same material as the primary mirror?
So it is another gold mirror, and it's a convex glaring mirror, about 2.42 diameter, I believe. Good question.
Yeah, thank you for that, Glitched Robot. So moving on, Amber, we've got a question from an 8th grade student who wants to know if JWST will be used to find or identify large objects in the Kuiper belt or the Oort cloud.
Absolutely. So that part of the outer solar system is something we're definitely planning to use JWST to study objects and to look for objects there. So like I said, the whole solar system, basically from Mars on out, is fair game. And so we absolutely will be looking for objects in the outer solar system with this telescope.
Wow. I mean, thrilled for what's to come. And unfortunately, that is all the time that we have for today. But Amber, Scarlett, thank you both so much for your time today. It was so great to hear your insight on this mission, and we really appreciate it.
Thank you. It was really an honor to share with you all.
Yeah, thanks so much. This has been fun. So exciting.
And a big thank you to all of you who joined and asked your question today. Make sure to stick with us as Webb gears up to unfold the universe and start sending back science and data. Visit go.nasa.gov/whereiswebb to keep up with the telescope's milestones, the observatory's temperature, and its location in space. The team will also be posting regular updates to the @NASA-Webb social media accounts. That includes Twitter, Facebook, and Instagram. We will be back to answer your questions live on this show once Webb releases its first images. So stay tuned and go Webb.
예, 듣기지만 감사하고요. 아마도 지금 제가 지켜보겠는데 6시에 미디어 지금 콘텐츠 컨퍼런스가 있는 것 같은데 한번 확인하고 제가 계속 알려드릴게요. 일단 이제 좀 돌리겠습니다.
Flight director today, he is at the helm and will be polling his team here for a no-go decision in about 16 minutes. Assuming all
lucky enough to spend exactly one leap year on the space station, 366 days. So you can imagine that in 366 days, you get to see the Earth quite a bit. Even though we are so busy on the space station, we do try to look outside and glimpse what's flying below us any chance we get. Was a part of me, the dreamer, the little kid that started dreaming about this whole experience now basically 40 years ago. That part of me was still there, unchanged for 30 or 40 years, and just marveling incredulously at the beauty of it all. And I would see clouds and green and rivers, and it would just completely fill my eyes. The difference in observing the world or the universe from inside the space station, looking through the windows, or being outside, is what I describe as the same level of interaction that you can have looking at a beautiful aquarium from the safety of a room. When you're outside and all you have is a helmet and maybe 1.5 inch of plexiglass in front of your eyes, you can see details and colors and shades, the level of detail that you can capture, and the way you experience that universe is going to be very, very different. You want and you feel that you have become part of it, and you can develop that sense of belonging. I think that the first impact of the first flight was that I did see and I did sense how fragile, how small the Earth is. We are used to think of the Earth as something so vast and big, and we don't think that what we do, our daily life, can affect such a vast system. But from space, you get a sense that every individual, every living organism is somehow connected. Seeing the city lights at night, where a place like